Okay, second video, topic 3. And here we're going to look at the stages of a Bitcoin transaction. There are 6 of them: signature, validation, building a block, proof of work, also called Nakamoto consensus after Satoshi Nakamoto, revalidation, and confirmation. So signature is when the sender of a transaction digitally signs and sends transaction details from a wallet. And we'll go through that, how they use their private key and what wallets they need in order to do that. Then the validation is the network relays and validates each transaction. And then once they've been put in a memory pool, the next stage is to build a block, and lots of miners are going to be building blocks at the same time and competing with each other. As soon as a miner gets a block, usually more than a megabyte when the network's busy, but they might decide to stop and start the proof of work puzzle when it's only 600 kilobytes. Doesn't have to be a megabyte. Once a miner has solved the puzzle, the first one to solve it will broadcast it to the network using the master nodes, and then the other miners need to check the solution, make sure that the transactions are valid again, and then once they're satisfied, they start building on that block, because it's a chain of blocks, blockchain. Okay, so that once the miners think that this block is okay, then they're going to start building another block on top of it. And it's confirmed, all the transactions get a confirmation. So if you've sent something from your wallet, you'll eventually receive something transaction confirmed. And that will mean that at least 51% of the miners have started building on the block that your transaction is in. So starting with the signature, it's a slightly different process depending on what type of wallet. There are lots of different ones. This is the Armory one, but you could have an Electrum wallet, or there's Parity, there's Geth. Those are mainly used on the Ethereum network. Anyway, so there's also 2 types of wallet: a cold wallet, which is offline. That could be on a USB stick, not even connected to a computer, let alone the Bitcoin network. A hot wallet is connected to the Bitcoin network, and so you need to have a hot wallet to send the transactions. So this pay to public key hash is a general process used by all the wallets. Although there are slightly different steps to follow, what goes online, what goes offline in your hot and cold wallets, the general process is you open your wallet and you input the transaction details. So that's your UTXO. It could be more than one transaction you've received that is going to go to one or more addresses. And if you don't spend it all on the fees and who you're sending it to, you would return the rest to you as a new UTXO. And then you put on your private key that you mustn't tell anyone and click sign, and that's going to hash it together, okay, using a cryptographic hash function that we covered in the last topic. So all the outputs are linked to specific Bitcoin wallets, and with this P2PKH, actually you're putting in not the wallet's actual public key, which is a 64-bit hex in Bitcoin, but a different 64-bit hex, but which is the hash of the SHA-256 hash of the actual public key. And it just makes it a little bit more secure. You don't have to do that, as I said, because it was only a soft fork. So some full nodes will be not using pay to public key hash. They'll be using just P2PK, but most of them would be using this because it's more secure. So the process of signature, let's look at this transaction 1 here. So owner of this transaction is going to send UTXO to owner 2. So they're going to use their private key to sign, and there's the signed transaction. And then all this is going to be hashed. This previous transaction where owner 1 bought the UTXO and the hash and the previous owner's signature is all hashed together. And that then goes into a hash that is hashed with owner 2's public key and owner 1's signature. And this is all passed on like that. Okay, now the validation. And this diagram here shows just one, these are the block headers, okay? And doesn't show the entire block. It just shows what's called the Merkle branch for a particular transaction. So in the validation, the light nodes will look up the input UTXO in the blockchain history, because when I'm sending it now, and this hasn't been built into a block, it hasn't been confirmed, but when I got it, it was confirmed, it was in a block. So that UTXO, say TX3, has a history. And that's what the light nodes do. They look up the history. So they find the hash of that transaction, they trace the hash, and then so the full node will just give them this part that they need to check that hash and this hash and that hash, and that everything was correct in the Merkle root. Now they know there wouldn't have been a double spend, because when this block was built, all the transactions in it were checked previously in the chain. So all they have to do is look up the UTXO from what that I put in, and linking it to a place in the chain that has got a timestamp. They know that the network has accepted it already, and that validates it. And then they put this transaction in the mempool. And then we get to the mining nodes, and these are the ones that are building a block. A miner will take many, many transactions, about 2,000 of them on average, and hash them all, and then take them in pairs. So one of the transactions will be his particular reward that he has digitally signed, and take the hash of that with one of the transactions and pair and pair and pair until you hash 2, 2, 2, and you get back to just one final hash which contains all the transactions, called the transaction root hash. And this is unique to the miner because different miners have different signatures. So this TX0 will be different for every miner. Even if by chance all these transactions are identical for 2 miners, this transaction root is unique to the miner. And also, it means that if somebody tried to change a transaction and make a transaction here, like transaction 2, and I send my UTXO to Walter, then if I then try to send the same UTXO somewhere else, then this would alter the hashes, would go, and the transaction root would change, because if you change just one of these, everything changes. So that's the general idea that was introduced by Satoshi Nakamoto in that paper in 2008. So just looking more at the elements of block, looking at the block header. So the previous hash, that's the hash of the previous hash, transaction root and nonce gets hashed and passed on to the next block. Now this is going to be something beginning with lots of zeros, and that's related to the difficulty, which we'll explain in more detail later. And this is the same for every miner, but as I said, the transaction root will be different for every miner. The previous hash should be the same, and sometimes it can take several seconds for transactions to be relayed around the world by the master nodes. And in some blockchains, not so much Bitcoin because it's slow, it's only 10 minutes a block. But when you've got 10 seconds a block, as in Ethereum, the latency might be a problem, which means that miners tend to work with different previous hashes. And that can lead to a chain that has sort of lacy, it's not a single chain like the Bitcoin blockchain. You could have things called uncles that go and come back to the main chain, a bit like if I've got a necklace and it's got another loop on it, yeah? Okay, so this is the consensus. Different blockchains have different consensus methods, but Bitcoin uses proof of work, also called Nakamoto consensus. And here, what happens is that the hash of the previous block and the transaction root for all the transactions, they're hashed together. And then the puzzle is to find the nonce. So another term from Lewis Carroll. So I'll talk about what a nonce is in a minute. Once they've found the nonce, they take the hash of everything, that becomes the hash of the previous block, and the details of the transactions in the block are broadcast to the network along with the previous block hash and the nonce that the miner found and the timestamp when it was found, and all the miners have to check that the nonce is correct, it did solve the puzzle. And then they confirm it and they can start building. So a nonce is a 256-bit hex, okay, 64 hex numbers, which when compressed with or hashed with the transaction root hash and the previous block hash, gives another 256-bit hex, of course, but it has to start with n zeros. And the number n depends on the difficulty of the proof of work puzzle, which we're going to call D in the next slide. So, for example, if n was 1, and you only had to find by trial and error, because you just keep hashing and hashing and hashing until you, by chance, find a 256-bit hex that starts with the number 0. Well, there are 16 numbers in hexadecimal, okay, 0 to F. So the chance that you get 1 0 at the beginning is 1 over 16. The chance that you get a 0 followed by a 0 is 1 over 16 times 1 over 16. Or because 16 is 2 to the power minus 4, it's 2 to the power minus 8. Or more generally, the chance that you find n zeros is 2 to the power minus, okay? So the difficulty, which changes with the hash rate, you can see here that the difficulty is growing all the time. And it can go down if the network's not, I mean, sometimes the hash rate goes down as well, as you can see here in 2019, and the difficulty also went down. But generally speaking, both the hash rate is growing as more and more mining farms set up, and so the difficulty does increase. And we'll, next slide, explain how we calculate the n from the difficulty. The difficulty corresponds to the probability of finding the nonce. It's different in different blockchains. In Ethereum, the difficulty corresponds to the average number of hashes, but we'll get onto that in the next topic. Okay, so this is the formula that the Bitcoin blockchain uses. It's a different formula for Ethereum. And 2 to the minus 4n is the probability that a random hexadecimal number starts with n zeros. The expected block time is called T, We know that that's 10 minutes, and that's to control the Bitcoin money supply. So it's going to run out more or less by 21,036. So if we take logs, we've got the log of D is minus 4n log of 2 plus log of t plus log of h, and turning it around for a formula in n gives log of h plus log of t minus log of d divided by 4 log 2. But also, because n is a number of zeros, it can't be a decimal, it has to be an integer number. So int is the integer part. So to illustrate that, suppose the hash rate at the moment is 130 etahashes per second, which is 130 times 10 to the 18. An etahash is 10 to the 18 hashes per second. And t is 10 minutes, which is 600 seconds. And if you looked at the previous slide, you'd see that the difficulty, current difficulty, was a very large number. It's something like 13,732,000,000, whatever, trillion. Is it trillion? Yes, trillion and 13 trillion. Okay. So anyway, taking logs reduces the size a lot. So the log of 130 times 10 to the 18 is only 46.3. The log of t is 6.4, and the log of d is 30.25. So if we do this sum here, we get 22.46. And if we divide it by 4 log 2, which is 2.773, the integer part is 8. So that tells us that with the current level of difficulty, the miners have to keep hashing until they find a hex that starts with n zeros. When you hash everything together, the previous block hash, the transaction root, and you add this random hex, and the result's going to be something with n zeros. So suppose a miner finds a nonce which, when hashed with the previous block and the miner's transaction root, gives this hex. Okay, this one is where difficulty is just 5. I mean, n is 5, so it's lower difficulty or lower hash rate. Then at that point, the winning miner timestamps the block, broadcasts all the data to the network, and then the full and light nodes work together to revalidate all the transactions in the block using these Merkle branches. And if they find an invalid transaction that has meanwhile been spent, when it was in the mempool, it was spent elsewhere as well, then the block becomes an orphan block, and the transactions are just returned to the mempool, all of them. So it's a bit wasteful. So that's called an orphan block. More than 50% of the miners need to indicate that they've confirmed that all the transactions are valid by building on that block. And they're going to work on creating a new block in the chain using this 0000, this random hex that you found with lots of zeros when you hash those previous hash, the transaction root and another random hex. So if more than 50% of the full nodes actually collaborate to say a block is valid when it isn't, in other words, they could refuse to confirm good transactions or they could confirm bad transactions. This is called a 51% attack. And here's a nice little video on the 51% attack. It's quite short.
You may have heard the term 51% attack, but what does it actually mean? Bitcoin miners use powerful computers to verify that each person who wishes to spend Bitcoins actually has Bitcoins to spend and isn't trying to fool the system. They do this by reviewing the blockchain, a digital file that documents every Bitcoin transaction ever made. Miners usually group together in mining pools so they can combine their mining power and become more efficient. The power of the miner's verification process comes from its decentralization. For example, let's say there's a transaction that is going through the blockchain. Each miner will review this transaction to decide if the sender actually has the Bitcoin he wants to send. If the majority of miners rules the transaction is valid, it will go through. But what if someone gets hold of more than 50% of the network's mining power and manipulate the system for his own needs? Theoretically speaking, if someone manages to pull off such an attack, he can double spend his money, meaning he can pay with the same Bitcoin twice or even more. The attacker will also be able to prevent transactions from being confirmed and prevent other miners from generating new Bitcoins. But more on double spending and confirmations will be reviewed in later videos. For now, here's a real live example of the 51% attack. In January 2014, one of the mining pools got so big, it neared 51% of the total mining power. This, of course, created some panic in the Bitcoin community, but was fixed shortly after by miners who left the pool in order to balance things out. One of the things to keep in mind is that someone with so much mining power would probably make more money using this power to mine legitimately than by actually blocking transactions or double spending. This reduces the risk of such an attack substantially. So now you know what a 51% attack is. For more information, please visit 99bitcoins.com, a non-technical blog about Bitcoin and cryptocurrency.
Okay, so that was a nice little video. So when it said the mining nodes check the transactions, what they meant is that the full nodes attached to the mining nodes and the light nodes attached to the full nodes would do that. The mining nodes just carry on mining. Okay, so when a new block is confirmed in the blockchain, the miners start again. The ones that they were building into a block get thrown back into the memory pool, and they're going to start a new block. They're not going to continue solving the problem that they were working on before because it may contain invalid transactions. They could have been confirmed in a previous block, they don't know. And anyway, the previous block header is the wrong one. There's a new block header they have to use. So that's why only one block is added to the blockchain. Eventually, I mean, it could be because of network latency that there are two being built at the same time, but then there will be one that becomes longer. So there's in the consensus, it's called the consensus chain, the longest chain, and a chain that isn't the longest chain will just get thrown back into the mempool. Now, this is why you can't cheat at Bitcoin. I rather like this. Say everybody's working on block 91, but one miner wants to alter a transaction in block 74. Well, he'd have to make the change and redo all the hashing, all those computations, and find the nonce, find the nonce, find the nonce, find the nonce, find the nonce. For, that's going to take a very long time. And he'd have to do it all before anybody else started building a new block. So that's impossible. That's why it's called work. Proof of work is the consensus name. So every time another block is built on this block, so block 74 to block 91, that would be 70, well, this isn't 16 confirmations so far, and this will be the 17th confirmation. And the more confirmations there are on a transaction, the harder it is for attackers to alter it. So a summary of these on-chain participants. For validation, you've got master nodes that relay the signed and encrypted transactions around the network, and the mempools. Most master nodes have their own mempools, and the miners work on that. Light nodes work with full nodes to check transactions have valid UTXOs. And then these are placed in the mining pool's mempool. Then in consensus, the mining nodes take transactions from their mempool into a block, and the winning miner will add the block to the blockchain. That's called consensus. And finally, confirmation, where the light nodes work with full nodes to verify the transactions in a new block, and more than 50% of the mining nodes must indicate that they confirm the transactions by starting to build with that block as the latest block. So that's it for this lecture, and see you in the next topic.